There is a relation between gravitation and distance. Now, that is something that made Isaac Newton scratch his head around it for a while, and he came out with an even greater equation than the Newton's laws of motion. Firstly, to be able to define the gravitation-distance relation, you need to head into the lab. In the lab, you have two objects, and you try to see how far is that object from the distance of the Earth center, and what is the magnitude of gravitation that is being applied on that object. So here you have the r, the distance from the center of Earth to the center of that object, and you do the measurements. Doing the measurements will form a curve. That curve is telling you the gravitational acceleration is reduced as the square of the value of radius is increasing. So the farther you are from the Earth's center, the smaller the gravitational acceleration. So in short story, there is an opposite relation between the gravitational acceleration and the squared value of the radius from the Earth's center. Now, Newton was looking into this relation and he said, well, I think we can create a universal gravitation law. Gravity affects all masses in the universe. That's what Newton's found back in time. No matter where you are on Earth or in outer space, you exert gravitational force on the object, and object exerts gravitational force equal magnitude, opposite in direction on you, based on the Newton's third law of motion. And because the gravitational force acts over any distance, the range of its effect is infinite. So near the Earth's surface, the magnitude of gravitational force exerted on Earth by object A on object B is given by the equation Fa on B would be mass of B multiplied by gravitational acceleration. But object B also exerts gravitational force of equal magnitude on Earth. Fb on A would equal ma multiplied by G. Newton hypothesized that given two objects A and B, the magnitude of gravitational force exerted by one object on the other is directly proportional to the product of both masses. So there is a proportional relation between F gravitation and mass of object A and mass of object B. And since we know there is an opposite relation between the gravitational force and the squared value of the radius of that object from Earth, that influenced him to be able to find the universal gravitational law. So if we look at an object have a constant mass, he's at this radius, then he go on this radius, then he go on this radius, away from the Earth center. So you have r Earth, you have 2r and 3r. So object 1 was on distance r, object 2, which is object 1 basically, but we move it to the second position, was on distance 2r, then he go on distance 3r. Newton realized that Fg here would be 1/4 of the original gravitational force on the surface, and it will be 1/9 of the gravitational force on the surface for the same object. That will be drawn in a graph on the xy Cartesian. You have here the distance from Earth center for the object represented as r, and you have the force of gravitation Fg. You can see here as r increase, Fg decrease, and as r decrease, Fg increase, and so on. Putting those relations together in one equation, you can see here that the Fg is proportional to the mass of A and mass of B, and it is in an opposite relation with the squared value of the radius from the center of Earth. So that can be represented as we find the proportion constant. We can say that Fg equal G, which is the proportion constant or the gravitational constant, multiplied by the mass of A multiplied by the mass of B over the squared value of the radius. This law is saying that any two objects, A and B, in the universe exert gravitational forces of equal magnitude but opposite direction on each other. The forces are directed along the line joining the center of both objects. The magnitude of the gravitational force is given by Fg equals G multiplied by mass of A multiplied by mass of B over r squared. It is simple but effective law. It's worth to mention that with the relativity of Einstein, this equation is being challenged. For most planets, this equation is still true, but there is some planets that the scientists discovered are not following this rule and considered an outliers. But still, in most cases, with some precautions and certain conditions, the universal gravitation law is still working. However, there is a room for new proposals for a new universal gravitational law that will follow the ashes of the theory of relativity of Einstein and be able to consider all the new scientific advancement. Then that law of gravitation would be more advanced than this law. It's worth to mention that it is relatively easy to come up with a new law in physics or in mathematics. Mainly in physics, you can easily come up with a certain law to describe a certain phenomena in physics. You just need to start in the lab, get the right tools, put your methodology, and try to get the right measurement or the right experimental tools that you need to be able to detect all forces and distances with high precision. And you try to look for a trend or for a certain behavior and relations between many variables. Then you'll be able to come up with an equation, and publishing that in a scientific paper or in a patent would allow you, until the scientific community digests that, it would allow you to have an approved new law in physics and change the physics as we know it today. It is easy with some dedication and more repeatable and accurate measurements and a trusted methodology. And you will be one of the brightest names in physics overnight. Here we have masses of objects away from each other with a certain distance. You have first mass m, you have distance of separation r, you have another mass, you have 2m here and r, and m here, you have 2m here and 3m here with r, you have half a radius here, m on the left and m on the right. You get the idea. So there is many variations of mass versus distance. How does that affect the magnitude of gravitational force? When you have two masses of the same size and a certain distance or radius, you have the force of gravitation would be some value Fg. When you have two or double the mass over here with the same mass over here and the same distance, you will get double the gravitational force that you get in the first case. If you get two mass here, three mass here, and the same distance, you get 6 gravitational force. And so on. You do the variations and you're able to come up with a table. If that was based on experiment and accurate instrumentation and measurements, you will be able to see there is a trend over here. That trend can be changed into relation. Relations can be changed into equation, and you come up with a new universal gravitational law, for example. So to summarize, universal gravitational law of the genius Isaac Newton, or could be the lucky Isaac Newton, is saying the force of gravitation between any two objects equal the gravitational constant multiplied by the mass of object A multiplied by the mass of object B over the distance squared. The first day I saw that equation back in school, I didn't like the idea that we're using r squared, because r is the distance. You know, when you are talking about a circle, you say from the center of the circle to the surface of the circle, that's an r. But when you're talking about the distance between two objects, r is not a relevant notation. You can feel free to replace that as d squared. This is the sun, this is the earth, and this is her moon. So the earth is rolling in a certain path around the sun, and the moon is rolling around the earth with a certain path as well. So if you want to measure the gravitational force between the moon and the earth, you measure the distance between the center of earth to the center of the moon, you find the mass of the moon, then you find the mass of the earth, and you will be able to find the gravitational force happening between earth and moon. What if you want to do the gravitational force happening between earth and the sun? You measure the distance between earth and the sun. Scientists gladly did that effort, and we know how far is the sun from earth, center to center. And you can assume the mass of earth and the mass of sun, and you know what is the distance, you know gravitational constant, you're able to find easily the gravitational force happening between the Earth and the sun, or the Earth and any other planet in the universe. Again, as we mentioned, there is some gravitational forces happening between the moon and the Earth. That force pulling the moon downwards in a constant way, that is keeping him from escaping his orbit. And as the Earth is pulling the moon downwards, there is a pair of force that's pulling the Earth upwards toward the moon. But since the moon is smaller in mass, the Earth is the one with the higher force. It's keeping him always in the gravitational field of the Earth.